Hello everyone. So we are going to start our session now. I will be giving a brief introduction about our speaker. So Dr. Kanti Manna sir is currently a lecturer of design engineering and program director of biomedical engineering at the School of Engineering, Design and Technology at Canterbury Christchurch University, UK. He is also a fellow of Higher Education Academy UK and a member of Association of Biomedical Engineers, Mechanical Engineers and Bioengineering UK. Apart from teaching and research, he is engaged in professional activities such as CPD, European HI3 network project. He has completed his bachelor degree from West Bengal University of Technology, master degree in mechatronics from Indian Institute of Engineering, Science and Technology, Sidhpur, and PhD in medical robotics from Bournemouth University, UK. His primary research interest lies in the area of variable exoskeletal for assistance and rehabilitation, sensor deployment for gait analysis, and VR-based technology. He was an academic lecturer position in reputed engineering colleges such as College of Engineering and Management, Kolaghat, and ITM University, Gwalior in India for more than 2 years. So far, he has published 21 research papers in reputed conferences and journal papers such as ICORR, DMD, SAGE, UK RAF, and many more. Currently, he is involved in several projects in collaboration with Kent and Canterbury Hospital, UK, such as teleneuro rehabilitation for delivering home-based remote post-op rehabilitation and respiratory hood for medical professionals. Uh, so today he is going to take a session on robotics and geopolitics, AI and national security. Over to you, sir.
Okay. Uh, okay, can you see my screen?
Yes, sir. It is visible.
Okay, thank you. Okay. Okay, first of all, you can call me Soumya, by the way, because we don't have this culture in the UK. So we call everybody by their name. So I'm very much comfortable. You can call me by my name. Okay.
Okay, sure.
So thank you. Thank you so much. So first of all, thank you, Dr. Jugal Dev, for inviting me to this prestigious FDP course on intelligent data analytics for critical infrastructure security. So myself, Dr. Manna, Soumya Manna. So I'm currently a lecturer in design engineering and program director in biomedical for the School of Engineering, Technology and Design at Canterbury Christchurch University. So actually, when I look at most of the contents of this FDP course, so I found out like I think 90% of the lecture are based on AI. So that is the reason I took out the AI from my presentation. I put the robotics only because that's my area of interest. So I will talk about robotics, and which is my specific area, which is nothing but exoskeleton, which is like an external muscle suit. And there are a few more other bit of research I have done. Now, in terms of national security, I'm not sure like how much that research can uh, overcome the problems faced by the national security, but I'll try my best to cover most of the areas that is required for the military defense and for the security purposes. Okay, so here it is. That's my academic background. So I always try to uh, cover from where I belong. So I'm actually originally from Calcutta, India. So I did my bachelor's in College of Engineering and Management, India, in BTech in Electronics and Instrumentation. And then I did my MTech in Mechatronics from Indian Institute of Engineering, Science and Technology, India. And then my PhD in Robotics from Bournemouth University. So before coming to UK, I was actually a assistant professor in one of the engineering college back in India. and then ITM University Gwalior for like 2.5 years. And I have joined in Canterbury Christchurch once I finished my PhD in 2019. And since then, I'm actually working as a lecturer and as a program director in biomedical engineering. Okay, so before starting my presentation, I would like to give a brief uh, glimpse of Indian geopolitical situation. So as all of us kindly our like our enemies and who are alliance, and they're all the tension on the border. So if we look at the north, so obviously we have a very finest friend, Pakistan, so who always give us a lot of troubles all the time. So we have faced a lot of wars, I think several wars, I would say, from 1962, and we are still in the time of war, and we don't know, anything could be happening anytime. So, and there's a lot of infiltration, and there's a lot of other tactical problems they always provide to us. At the same time, on our right hand side, on the north east side, so it's China. So we have recently had a clash in Galwan Valley, so like at the line of control. So they already occupied a lot of portion that's called Aksai Chin, but they are now trying to occupy more areas, which I think their mentality all the time. And if we are currently aware of current situation where the Afghanistan is taken by the Taliban power, so in that case, uh, the Pakistan have got much more advantage in terms of all those terrorist activities. So considering all the situation, obviously we have to enhance our national security, at the same time our power in the defense sector, or power in the military, whether it's an army, uh, air force, or navy. So considering all the situation, uh, we have to think about how the technology can help us. Yes, of course, we need money for that. But at the same time, how the different types of advancement in the technology, different types of cutting edge research in the technology can actually support us to tackle all these issues. Because obviously, if we have, let's say, we have enemies like Pakistan and the China attack us all the time at the same time, then obviously we have to give the reply back to them. So what would be the technical perspective in this current scenario? So then the question comes, do we really need robot? Yeah, robot is a kind of very fascinating word we all probably faced during our childhood, at the same time when we studied, and we have tried to do something in the robotics areas, probably myself, Dr. Jugal, and I think a lot of you, making line tracking robots and like humanoid robots. Now, in terms of applying robots in industries, or let's say in the defense or national security sector, can we afford it, first of all? Because in the country of 1.4 billion, where people have to face a lot of problems regarding their basic necessities, they have to invest, let's say, 70 to 80 billion pound for the defense sectors and other development purposes. So is it necessary for us to implement a robot for all the national security and defense purpose? This is the first question to all of you, and to all of us, actually, I would say. So let's try to find the answer first. So these are the tasks that needs to be performed in the battlefield, whether by the soldiers or by the other security personnel. So the first task that I think that's mostly all of us are aware of: intelligence, surveillance, and reconnaissance, ISR. And next, that will be search and rescue. So sometimes the army people, they have to go for a search and rescue operation, even for different hazardous conditions. At the same time, for the natural calamities. Combat support, I think that's one of the main tasks and important one the defense people have to perform. The mine clearance, like a lot of mines, so whenever they are going for some scouting operation, so obviously they have to first of all track the mine using some metal detector or mine detector, and then you have to clear it. And of course, there are some other issues like firefighting. So, okay, those are the tasks. Now, uh, we have to find out like how those tasks can be provided from a robot in terms of a human personnel. So for that, I have created a scene. So I took that picture from one of the blog. So thinking about a scenario in a battlefield where a group of soldiers is going towards for a certain operation, and suddenly one ID blast or some grenade attack or some bomb attack. So in that case, of course, there will be a lot of casualties. If we look down back in our history, in the last Kargil war in 1999, we have lost more than 550 people, and almost I think 1,300 people they are injured, severely injured. So some of them they paralyzed completely, some of them lost their limbs, and lot of soldiers they are literally they are become vanished in that sense. Actually, they have been captured by the enemy. So sometimes we just forgot those things like okay, what happened there, it's their duty, but think about their family, so what they have lost. So in that case, can we overcome those losses by implementing some robot? Okay, so this is our question. So that's what I told you at the beginning, like let's find the question, do you need a robot in the national security or defense sector? So can we overcome those losses using those robots? So for that, another statistics I would like to talk about, that's the medical issues the veterans suffer by the race. Like, of course, there will be death casualties. That's, I think, the ultimate casualties faced by the soldiers. But at the same time, when the soldiers, whether they're in the service or they are actually returning from the service, they literally had a lot of issues, whether hypertension, lipid disorder, diabetes, hearing problems, uh, some dermatologic problems, refraction disorder, cataract problem, eye, spine disorder, depression, all those kind of things. At the same time, I don't know whether you're probably aware of, like if a soldier normally spent more than 4 to 5 months or more than 6 months on Siachen Valley. So literally there is a situation called frostbite. So suppose in it by any incident, by any accident, if the ice come into the shoes or in the hand, so normally that become numb, and they literally have to cut out that particular limb to avoid cancer and the gangrene. So literally, sometimes if they spend more than 6 months, they literally lose certain fingers or on the toe from the foot. So that's the reason they normally cannot stay more than 3 months. So these are the kind of problems they have faced on the battlefield from on the war zone. At the same time, if we just looking after the cost, so to account the increased lethality of the war, a vast budget is required to maintain the active duty army. So that's an example from the US Army. So simply recruiting and soldier cost around $1,500. That's quite huge. It's almost like 10 to 12 lakhs in Indian currency. And the cost of treating an injured soldier, US soldier, is about 2 million a year. That's from one of the journal in 2014. And if we look at the Indian military expenditure, that is, I think last year it was 72.9 US billion dollar, where a large chunk of Indian defense budget go towards the salaries of around 1.4 million serving personnel. So the question I have actually raised at the beginning, so can we replace those personnels with the robots? So because as you can see, we have to spend a lot of money only for the salaries and for the pension. So that's some statistics in 2017. For example, 67% of the defense budget went towards those heads, and only 33% was spent on the new acquisition of hardware and equipment. So then the question comes, okay, if we replace those soldiers with robots, then what will happen for their livelihood? So obviously in India, like, the employment is a big issue. So if, let's say, if we make more than 1 million soldiers jobless, then what would happen? So obviously we have to create a certain sector to re-employ them. Or do we have any other solution? So that is the reason today's topic I focused on, of course, like the autonomous robots for the military operation, the surveillance, that a lot robots that has been developed or underdeveloped. And also there's another research area which I am currently working on, that's called exoskeleton. So the exoskeleton is nothing but like an external muscle suit a soldier can wear, and that can enhance their muscle strength. Okay, so that is something we can think about. We probably don't need to replace the human personnel, but by wearing that robotical arm or robotic suit, that person can enhance their strength, let's say by 5 to 10 times. So in that case, the job problem is not a issue anymore. So I'm going to talk about that. So first of all, I'll start with the autonomous robots for the military operation and surveillance. So those are the topics I'm going to cover. What is the need, the types, the working, few examples, and the scope of future research. So that's what I talk about. The first of all, the job of a soldier to carry a huge load in the war zone, rescue people from hostile environment, walking through the minefields, operate in unstructured environment with live risk, of course, and the carry out complex operation in battlefield with smart intelligence. Now, how the robot can support those activities? So a robot can replace a military personnel and can do most of the jobs instead of humans, such as it can carry 10 times of the load a human can. It can operate in a dangerous mission with much more accuracy, speed, and precision. It can provide more benefits with inbuilt sensor interfacing, because all of us, we know, so if we, let's say, put some inbuilt cameras, laser sensor, radar, GPS, other inertial sensor, so literally we can almost monitor all kinds of activities outside, whether it is some environmental measures or some other security measures from the enemy. Also, we can implement the human intelligence in the inbuilt controller with small control system. So I think probably my last speakers, they have already talked about this AI, machine learning, and all the genetic algorithm. So you can understand how we can implement the artificial intelligence to make the common system smart enough so that they can behave like a human. And also, I think that is one of the most important thing. We can bear the cost of making the robot instead of losing a human life, which is, I think, we cannot compare with any kind of cost, literally. So today's robot, I think most of the robots in the defense sector or in the security purpose normally been designed for the specific purposes with advanced specification. Sometimes instead of AI control fully autonomous robot, we have the systems which is controlled remotely by the human operators, who is situated somewhere in the ground station. So we can actually divide those unmanned vehicles, those remote vehicles, by 3 types. One is called unmanned aerial vehicle, that's called drone, that's another name of it. So unmanned underwater vehicle and unmanned ground vehicle, based on 3 different regions. So of course, air, water, and ground. So obviously, how can it replace, in a way, how can it replace Indian Army, Indian Air Force, and Indian Navy? So this is a one forecast about the drone market size from 2020 to 25, taken from one of the latest journal. And as you can see, the revenue by 2025 in the Asia, that will cross more than 40 billion dollar. So we have to think about it. So it's not the other people, they're not mad. So obviously there is some other advantage that actually happening if we can integrate those robots. What is then the components of UAV? So the components of UAV, the automatic aerial, the unmanned aerial vehicle. So the communication system, the navigation, the monitoring, the obstacle avoidance system, and the weather system. So you can see we are actually kind of integrating a lot of smart features into it, smart system into it, so that it can actually have much more intelligent behavior. So in terms of communication system, normally it normally used in the ultra high frequency. It communicates with the KU band system. So KU is nothing but that's normally the band, the frequency from the 12 gigahertz to I think 15 or 14 gigahertz, and that's normally used by the satellite communication. So for an example, it normally operate in the uplink frequency of 15.15 to 15.35 gigahertz, and the download frequency of 14.40 gigahertz to 14.83 gigahertz. For the navigation, it sometimes do use the GPS or global positioning system for tracking the positioning points when they are trying to track a certain areas. At the same time, WAS, wide area augmentation system, that's actually based on GPS. So that's a augmentation system created by the US people. And also there is another augmentation system that's called local. So that's we can use for positioning and the navigation purposes. For monitoring, we can use the GPS, at the same time stereo camera, high resolution still and video camera. Obstacle avoidance system, simple air traffic alerting system, and ground proximity alliance system for that. And weather system, we can the normally UAV use the weather radar for measuring the precipitation and the humidity outside the UAV. So UAV developed by the India. So if I'm talking about India right now, normally the DRDO, HAL, the Hindustan Aeronautics Limited, and the ADE, that is nothing but Aeronautical Defense, I think, establishment. So that is one of the organization created by the DRDO. So from DRDO, there are two, I think, model they have developed so far, Luxor and Rustam, and they have several versions of it. I think Rustam, I think currently is Rustam 3 under development. And from the ADE, there is another 3 UAV they have developed. That is nothing but the Fluffy, Pawan, and Nissan. So this is one of the finest UAV developed by the DRDO, that Luxor. And these are all our features. So it features a breakable nose cone, air target, imitator, infrared sensor, synthetic aperture radar, jet rocket booster weighing 150 kg, 145 kg is installed to enable smooth takeoff. It can climb at the rate of 25 meters per second, and the maximum speed of the aircraft is around 857 km per hour. And the range of the servicing are 150 kilometer and 9,000 meters respectively. It can be controlled from the ground control station, GCS, through pre-programmed hardware and software system. And it is powered by a single PAT7 turbojet engine. So it is one of the version created by the HAL that has a capacity of 3.7 kilonewton of thrust. So it installed the flight control electronics, electromechanical actuator, vertical gyroscope, and acoustic miss distance indicator that actually used for defense and flying, maintaining, and I would say kind of training purposes. and also the continuous wave Doppler, CW. This is another UAV also developed by DRDO, that's called Rustam. So it is a medium altitude, long endurance unmanned aerial vehicle, UAV, designed to carry out the surveillance and reconnaissance roles for the Indian Armed Force. It is capable of carrying different combination of payloads, including radar, electronics intelligence systems, and simulation awareness system. It has an endurance of 24 hours and at present is capable of reaching at an altitude of 23,000 feet, which is quite good enough. The maximum speed is around 150 km per hour for Rustam 1 and 225 km per hour for Rustam H. Okay, so the new model that came, I think, in the market currently, Rustam H. There are some other types of UAV. We probably have seen those videos a lot on the YouTube. So that is one a kind of UAV. It's called aerial blimp. So it's quite a big balloon-shaped system where normally it can be controlled from ground using remote, using rear control operator, or sometimes if it is quite big enough, then obviously the human operator, they can sit inside it and they can control it. And there is another, I think, quite popular item among us, that is like quadcopter. So that currently used for even the entertaining purpose, and if we come to the defense and security sector, it can be used for the surveillance purpose and sometimes for carrying small objects. Obviously, it cannot carry a huge payload because of its own capacity. So I think there's the video, so I can play. So as you can see, that blimp actually been used for carrying a lot of quadcopters inside it. So normally what happen, if we use another a big I think aeroplane or big helicopter for carrying those quadcopter or those items, and suppose the enemy strike those helicopters, so that's actually cost almost more than few million pound or few million, I think, Indian currency. So in that case, the cost factor will be, I think, 100 times reduced if we create this kind of blimp, because that's a blimp. It normally put hydrogen and helium inside those balloon for getting the thrust, and also we can add all the other items inside it and you can control it. So literally all the money we are spending on other buying all those big airplane for carrying and the helicopters, we can actually overcome those problems. The same time, the quadcopter is quite a popular, you probably have seen. So mostly what we normally do, we normally fit a stereo camera or an RGB camera underneath it, so that whenever we are flying those quadcopter on a certain areas, we can actually monitor and survey that area map. At the same time, like more other sensors can be included, like moisture, humidity. Also, what I've seen, I forgot to include that video. I've seen one quadcopter. They literally included a small gun with that. So that can be used as a weapon. So suppose if you're just flying that quadcopter on the enemy base, and you can literally target human or probably a certain smaller target one with this kind of system. So by the advancement of this kind of technology, we literally don't need to send somebody for the operation. We can send some this kind of blimp, quadcopter, or UAV to the enemy base, and we can actually tackle those issues. So again, the next features, of course, we have covered the aerial one. Now the other one is called unmanned underwater vehicle. So this is for underwater. So of course, like we know, most of the time we normally use the submarine for the surveillance, at the same time for the attacking and the dealing in a war zone. So in terms of using a submarine, because it's submarine, if I'm not aware of, I think it's more than, so last submarine INS Bikram, it cost more than, I think, 200 million, or probably somewhere near the billion, 200 million, or I think somewhere near the billion US dollar or pound. So in that case, can a robotic device can serve this purpose? So that is, with that aim, actually scientists have developed unmanned underwater vehicle. So that is a robotic device driven under the water by the propulsion system and operated autonomously by the human operator on the surface. So these are the other types of underwater vehicle. Okay, based on the type of function like ROV. So when the underwater vehicle is controlled remotely uh, from a ground station, that is called ROV, remotely operated underwater vehicle. And when the underwater vehicle is completely autonomous, that means it can perform indigenously and independently. In that case, we are calling it AUV. So I'm going to play this video.
Deep sea operations can be more challenging than space.
Okay, before playing that video, may I ask Dr. Jugal, can you hear the sound? Hello, Dr. Jugal?
Yes,
Can you
yes,
hear?
sir.
Yeah.
The thing is,
Can
like, it's a bit low. Can you please increase the voice?
Yeah. Okay. I think that's the maximum. Okay. What
I think it should be fine. But we
so
can
what I'm
hear
asking
the,
is,
yeah, but we can hear the voice, so not a problem.
okay, so when I'm playing the video, can we hear the sound? The audience?
Yes,
Yes,
yes.
yes, yes. We can hear the sound.
Oh, okay, that's great. That's great. Okay.
Deep sea operations can be more challenging than space exploration. When astronauts sent messages from the moon, there was a 1.2-second delay before they were heard on Earth. Yet when aquanauts sent signals from the Challenger Deep, they took 7 seconds to be received. Only the most advanced technologies can help us explore this complex frontier. Underwater inspection and monitoring are essential for many industries. Operators deploy professional divers and ROVs, but their effectiveness is limited, especially at great depths or in rough seas. As maritime operations expand into deeper waters, more remote locations, or more complex conditions, operators need more intelligent, safer, more cost-effective solutions. Autonomous underwater vehicles, or AUVs, are wireless robots that can safely perform complex tasks, potentially at lower costs than divers and ROVs. At TNO, we apply key technologies that enable AUVs to be deployed for autonomous maritime inspection and monitoring. Let's explore how this works. The TNO Vision uses acoustic signals for underwater communication. We develop high data rate solutions for wireless streaming of rapid, high-resolution sonar images and compressed videos. We also created underwater modems and designed mission planning software to determine where to best deploy the modems to create a communication infrastructure. Next, we enable multiple AUVs to cooperate with each other. Now, we are ready to begin our mission. We use 3 AUVs to inspect a selected area of the seafloor. If one vehicle fails, another vehicle can take over its tasks, and as autonomy improves, even less operator interaction will be needed. With TNO, you can use the latest technology and AUVs to make your underwater operations safer, faster, and more cost-effective. Are you ready to deploy wireless solutions for your maritime operations? Get in touch with TNO Maritime and
Okay, so this is the AUV developed by the TNO Maritime. So I just want to show the working principle of this AUV system. So as you can see, so it is capable of surveillance, it is capable of monitoring, it is capable of doing small activities. So with that advancement of technology, if it is that AUV can able to carry more payload, so literally like the other submarine, we can also launch uh, attacks from this AUV itself. Okay, so these are the components usually, but of course for the UV, but of course based on the different model and the different security purposes, more features normally been included. So the sensors like compass, depth sensor, side scan, sonars, magnetometer, thermistor, those have been used for monitoring purpose, and for the navigation they normally either use the GPS or underwater acoustic positioning system. So as you can see, uh, for the underwater acoustic positioning one, so they normally use the transponder. So it is kind of similar like the buoy on the top surface of the ocean. So those kind of similar thing normally integrated on the sea floor. So suppose if the operating, if this kind of UV operating within the net of the seafloor deployment baseline transponder. So this is called as LBL. But when the surface reference is available, such as on support sea, then it can be called as a ultra short baseline USBL or short baseline positioning system. Sometimes we normally can use the inertia sensor, such as the inertia sensor is nothing but is a combination of accelerometer and gyroscope. Sometimes the digital compass is also integrated with that. So with this kind of system, they can compute the position based on this motion sensors, like they can measure the accelerometer, the gyroscope, that can show about the orientation, like how much tilt that system has, whether left or right hand side, up or down. At the same time, the digital compass that can provide the direction and the orientation of the EUV. For the propulsion, it's normally been used propulsion thruster driven by the electric motor most of the time, and the power by the rechargeable batteries such as lithium ion and lithium polymer. Okay, so before moving, so these are all the kind of generic features. I'm not saying this is only the components that is used for the UV, but this is the kind of general components. But at the same time, based on the advanced UV, so those are quite classified and for use for the security one. So obviously they have more items and more sensor systems and more advanced control features in it. So this is one of the indigenous UV, AUV actually, I would say autonomous underwater vehicle developed by the India. So that's called, that's the name is Maya. So it is an automatic underwater vehicle developed by the Marine Instrumentation Division of the National Institute of Oceanography, India. And the vehicle has the endurance of 7.2 hours, and total length of 1.7 meter and the diameter of 0.234 millimeter. And it is propelled by a single rear thruster, and the navigation sensor include like Doppler velocity log and MEMS inertial measurement unit. Okay, so this is a kind of, this is an Indian's own product, but also as I can remember, there is another AUV. So when I was back in 2013, so I was engaged with one of the CSR lab that's called CMERI. You probably heard about that name. That's called Central Mechanical Research Engineering Institute. So it's situated in Durgapur. It's situated in Durgapur. Basically, they have developed one AUV for their research purpose, and they have also deployed it with the National Institute of Oceanography. So also, I think there is another news that came. I think now the L&T defense sector is also deploying, and they are actually kind of creating new product. They also created another AUV. I think that's I forget the name. That's called Amok, or so they also kind of now including their research now for the defense purposes. Now the unmanned underwater vehicle. So we have already covered what can be the robotic device that can be implemented in the underwater, at the same time in the air. Also, I think this is one of the most important field where the robots should work with, because most of the cases the war normally fights on the ground. So how can we use an unmanned ground vehicle so that can actually operate in the similar kind of situation a soldier is facing? So an UGV, that's called unmanned ground vehicle, it can operate on the ground and without an onboard human presence. So it can be used for many applications where it can be maybe inconvenient, dangerous, and impossible to have an human operator present. So it can have a lot of sensors to observe the environment and will either autonomously make the decision, like it is if it is autonomous purely, or pass the human information to the human operator, the different location which can control. So it is like control from the ground station. So this is one of the example of UGV, unmanned ground vehicle. I can play the video. You can probably, so it is one of the UGV developed by the US Army. So as you can see, a machine gun is fitted on the top, so it's kind of looking like a tank, but yes, of course, it is much more lightweight. So as you can see, it is remotely operated from an operator. So if they have a camera in front of it, they can see the outside and they can track as per the requirement. And it can also travel on the uneven terrain, where actually the most of the cases, the war zone and the other battlefield does not have like a smooth surface. So obviously the vehicle should be capable enough so that it can go over the uneven and the unknown terrain, of course. Yeah. So it can even travel over the stairs as well, like a human can do. So it's a machine gun fitted on the top of it with another gun in front of it. Then there's a RGB and the stereo camera with the radar positioning system. Okay, so a few features of the UGV, that's mostly it has stereo vision camera that can actually measure the color image, at the same time the depth image. So we can also get the depth information. So suppose an obstacle or any enemy in front of the UGV, so how much distance it is, so we can also measure that one. It has a color camera, radar, the radio detection system, and the ladder. So this is a kind of laser detection system. It has more advantage than the radar. Then the GPS, of course, the global positioning system. Most of the cases, it has an onboard CPU for like the central processor unit for mapping the landscape and control the mechanical activities. If it is remotely controlled, in that case, normally the information being transferred by the radio signal from an operator through that CPU, and then the CPU perform this action. But if it is autonomously controlled, that means no human operator, so the UGV is actually kind of controlling itself independently. In that case, it is being controlled using a smart algorithm, so that based on the situation, they can take the action, with the reference to its predefined, of course, function, because we have to pre-program it before, like if, okay, there's an enemy, of course, you have to start your gun. If there's an, like, of course, an object that is a still object, there is no point of wasting the gun. And the measurement unit, normally they have like altitude, position, direction, and orientation. They can use like in initial, sorry, it is inertial measurement unit. So sorry for the spelling mistake. So that's a combination of accelerometer and gyroscope. And also, as you can see, sometimes it has connected some articulated arm in front of it. So suppose what it has to do. Let's say, and we are sending an UGV to carry a certain object, to pick and place, or to take out a grenade, throw it somewhere, or maybe sometimes to just kind of carry a wounded soldier from the battlefield. So in that case, this kind of articulated arm will be a great help for this UGV. Okay, this is one of the UAV. Actually, it is autonomous vehicle, unmanned autonomous vehicle. It is Mars. It is a kind of it is actually ground vehicle as well. It is created by defense tech startup Taurus Robotics, and this Mars, that's the full name is Mobile Autonomous Robotic System. So they are actually implementing these robots for the Indian Army as a ground underground unmanned ground vehicle, and they are actually been working since 2019, which is quite recent. But also at the same time, now the companies like Ashok Leyland and L&T, they're also participating in the defense sector to create this kind of ground vehicle, unmanned ground vehicle. Okay, now we have talked about all those kind of quite robotical system, but now there are other research lab like Boston Dynamics. They literally created something you cannot even imagine. So like a simple human. So suppose think about a person, he's a robot actually, and he's basically working like a soldier. And that is why right now there's another field of robotics that is being people are researching in it. That's called bio-inspired robotics. So that can be used for the surveillance and other works in the war zone. So all these 4 robots has been developed by the Boston Dynamics. So I'm going to play the video each of them, and then you can see like how the robotics can be used in the battlefield, in the defense sector for the security purpose. So let's play this video. So the name of the robot is called Atlas. So you can find a lot of videos in the YouTube, and if you go to their website in the Boston Dynamics, you will find the more features and the function of this kind of robot. So by the video, as you can realize right now, so how the robotics has been developed. So literally they can actually use this kind of robots as a normal human personnel in the battlefield. Okay, so there's another robot. It's called it's a wheel robot. So that probably have more speed. Suppose if you have a smooth terrain where you can use this kind of robot. And as you can see, looking at the dynamics of this kind of robot, like how balanced they are. So literally the kind of advanced and adaptive control system has been used for this kind of purposes. So they are actually having this gravity compensation algorithm inside it, so that suppose if it is changing in alignment, so that it can actually put some counterweight on the other side to balance it front weight. Okay, so as you can see, when they are leaning towards at the front, the counterweight kind of balance it back. There's another video, it's called Big Cat. So this is a kind of bio-inspired robot as well. Big Dog, actually, sorry for my mistake. So it's a kind of dog like features, but it's a robot actually. It's fully autonomous. So that can go in a war zone, or for like in enemy areas, that can go for an surveillance purpose, monitor the people, and literally look at the balance. And if it has been destroyed by the enemy people, yeah, it's a cost a lot of money, but at least we can save a human life. Now, the similar kind of big dog now been integrated with an artificial robotic arm. So now, along with going with on the battlefield, it can also perform some tasks. So you can see that video that has a camera in front of it, so that can pick a certain object. So that, so you can see their function, how they can be used. So they normally use, so this kind of robotic manipulator is called serial manipulator, where all the robotic arm is normally been connected serially. So that's a part of kinematic robotics that's been used. At the same time, there's another type of robotics that's called parallel robotics, the parallel kinematics. So where this robotic arm that can be based on the parallel manipulator. But this is a serial one. You can see the video, and there's a gripper at the end. So that gripper is been controlled from the onboard CPU. Look at the power. So literally it can also drag almost like 10 kgs of load quite easily. And the precision they're performing. Boston Dynamics, they're writing, okay. So the gripper in front of it, of course, like they have used a specific purpose gripper because they would like to pick and place certain object. But at the same time, as our robotics people, we can actually change the gripper. So literally we can use something like a pneumatic gripper. So that can use the suction technique for gripping an object. At the same time, we can use some other types of gripper. So obviously, based on the requirement, we can actually change the design. Okay, this is the collaborative robot that's in our university in Canterbury, Christchurch. So we have tried to program it. So this is a ground-based system. So the first one, I have programmed it for just moving from one point to another point. And the second one is like kind of tracking the item on my hand, and then it can actually pick and place that object. So let me play that video. So that robot is actually programmed for, that robot actually programmed for just for moving from one point to another point following a pattern. So as you can see, that actually following a certain pattern like a zigzag. Now the second video actually it can not only moving from one point to another point, at the same time it can pick and place a certain object. So it's a predefined points, but we can also program. So that's me actually. So we can also program accordingly, like it can track my human arm, my hand position, and it can pick that item from my hand and place it. So it's one of the robot we have. So we have almost two robots. One is this one, this SWA robot, and another we have that's from the Mitsubishi. So we can use this for even for this kind of defense purposes as well.
What you're looking at could be the soldier's uniform of the...
Now, the last time we have talked about, yes, we can replace the human personnel. What about without replacing, can we enhance their strength? So look at the picture. As you can see, the soldier actually wearing an external robotic suit. So what happens, suppose if a person is wearing, suppose if somebody can load, somebody can lift, let's say 10 kg of load, and in battlefield, like you don't need to carry a 10 kg of load and just lift down, not like this. So sometimes they have to carry a huge amount of load on their back, on the front, for let's say few kilometers. Sometimes they have to carry their wounded soldiers, their friends, their colleagues. So in that case, what happened for a normal human person, of course your muscle become fatigue after a certain time, so it become tired, then drug. It's a normal human nature. But can you use a robotic suit along with you to enhance your strength? So it's I won't say, but this is a kind of making you like a superhuman. So suppose if you can lift a 10 kg of load, but with having this robotic suit on your hand, on your arm, or on your leg, literally you can lift around 50 kg, and that quite with ease, literally. At the same time, suppose with in a normal human person, like if a soldier can travel, travel, let's say 10 kilometer without any tiredness, but at the same time that can with this suit they can travel around 50 kilometers. Because what happened, whenever the soldier is wearing the suit, most of the torques, like joint torque and most of the joint range, that has been taken by the outer muscle suit rather than the human itself. Let's play the video, then you can get an idea how does it perform.
Future. Not too distant future. This is the exoskeleton, now being developed by Raytheon, newest research in Utah. The exo is a robotic suit that gives its wearer greater strength, endurance, and agility, just like the superhero depicted in comic books and Hollywood movies. Think of the exoskeleton as an amplifier. Raytheon engineer Rex Jameson says it's easy to use.
Oh, it's very natural. You can get it today and walk around. I like the quick movements, like the speed bag and playing soccer with it. And some of the power stuff, it can carry 150-pound payload, walk up ramps and walk upstairs.
Raytheon Sarcos, a leader in advanced robotics, is developing the exoskeleton for the U.S. Army. The suit is a combination of sensors, actuators, and controllers, all packaged in this futuristic design. Dr. Stephen Jacobson heads Raytheon Sarcos and this project. He believes invention is a combination of art, science, engineering, and design.
Scientists, whatever, but it's not us. It's a process of getting together, understanding the problems, human designing something to satisfy the needs.
With the exoskeleton, Raytheon is not only satisfying a need, the company is pushing the boundaries of technology. Science fiction will one day meet reality.
Okay, so as you can see, so this is a kind of external muscle suit. So that is why it is called exoskeleton. So exos, that means outside, and skeleton means your human body. So that's my research areas actually where I did my PhD. Okay, and this is the market of robotic exoskeleton. So from G Gardeners, and as you can see, the market is rising. So by 2025, the number of sales estimate that will be around 1,20,000 units per I think year, and also it can be increased more. So based on the defense budget, of course, as you can see right now, the situation is quite fragile. So of course, like anytime the war can be happen between the two countries. So with this kind of situation, obviously the implementation of this kind of robotic device can provide a huge help. So the types of exoskeleton as I'm talking about, so usually it can be divided into two types. One is ground-based system, that is called, one of the example is Armin, that is developed by the University of Zurich. The other is the body-based system. One is that's called Titan Arm, the University of Pennsylvania. So it's a kind of portable system the human can carry itself all the time. So these are the properties, I might say, basic properties of a robotic exoskeleton. The functional properties, the technological characteristics, the financial benefits, and the psychological benefits. So the functional properties, of course, like the structure of the whole body. So suppose if we like to create a exoskeleton suit for a human person, so we have to think about how the human body looks like. Suppose if we are trying to think about we are making a suit for a human arm, then we have to think about how many degree of freedom that human arm have. Okay, how much length? So what is the length of our lower limb, upper limb? So biomechanics, how much load we can lift? Okay, so those are the things we need to consider whenever we are kind of making an exoskeleton. Portability at the same time, because obviously if we are talking about a soldier carrying itself, so it should be portable. It's not something like the soldier situated at the ground system and they are doing that activity. So of course you have to think about the portable system. Safety, I think this is one of the I think important factors before everything. So that is why most of the cases when you are developing any product, even for the human users, we have to think about the CE mark, the safety part first, because as you can see that all the exoskeleton that has a motor outside that actually helping the human joint to lift that certain object. Now, of course, the motor is quite powerful. So anytime any malfunction happened in the exoskeleton, so obviously that can even break your whole arm or your human joint. So you can think about if something wrong happened, instead of helping you, it will literally make you paralyzed for your whole life. So we have to think about its safety. Safety in that sense, it should be safe from the electromechanical and from through the soft computing. So electromechanical in that sense, we have to think about some limit switch, some boundary condition in the mechanical actuator. At the same time, whenever we are programming this kind of robotic exoskeleton, we have to program in a way so that it may not go beyond the certain boundary. The weight and size, so of course if it is too much weight, even the users cannot carry, then there is no point of developing. And the size itself, because it needs to be fit with that human body. Ease of wearability, so suppose the human personnel, a soldier is carrying it, let's say for 8 hours long, so it needs to be wearable, because otherwise after 1 or 2 hours it becomes painful for the user. So of course they may not use it in the battlefield, because sometimes the soldier needs to spend more than 3 or 4 days, okay, outside without any food or any either drink. So in that case, that exoskeleton needs to be wearable by them. Comfortability, so that's a kind of, I would say, quite close to the wearability. Now technical characteristics, we have to think about few technical characteristics, like torque to weight ratio. So most of the cases, if we are making a portable structure, the torque to weight ratio should be good enough so that it can make it portable and lightweight. And degree of freedom. So degree of freedom is one of the main criteria, because if we are thinking about a shoulder joint, it has 3 degrees of freedom. So it can move in 3 directions. At the same time, it is an elbow joint. It has 1 degree of freedom. That means 1 direction. So if you're thinking about a robotic arm that has 7 DOF, so that means if you are thinking about a lower limb like a hip joint, that has 3 degree of freedom. If we have a knee joint, that has 1 degree of freedom. If you have a ankle joint, that again has 2 to 3 degree of freedom. So obviously, if we are making an exoskeleton for an human arm, human whole body, we have to think about the degree of freedom. So degree of freedom is a way we can think about in generic sense, like in how many direction your joint can move independently. Now, of course, the battery life and energy efficiency, because what happened, suppose if you are carrying it for, let's say, 10 hours, so your battery should be good enough to provide the power to all the motors that is on the joint. The control architecture, like the control can be manual, can be semi-automatic, can be full automatic, can be adaptive. So manual means in fully manual, semi-automatic means partial manual, partial automatic, fully automatic means we don't need to think about anything and the robot can take care of itself. Adaptive means this is actually coming with the more adaptive natures, adaptive features, where suppose the exoskeleton is with the soldiers is moving towards any unknown situation where they are not even familiar with those situations. Let's say suppose they are going to a Siachen glacier, so the normal temperature is minus 60 to minus 70. So in that case, if in that situation the motor does not work and the control system that got stopped working, so then what? So of course the control system should be good enough and adaptive enough so that they can get adaptive to the unknown situation. The financial benefit, of course, if we are kind of thinking about a bulk number of items, we have to think about its purchasing cost, the repairing and the maintenance cost, because let's say if we are ordering 10,000 of pieces, so we have to think about that budget as well. Psychological benefits, okay, we normally ignore that part, but most of the times it's a play a important role while taking all those exoskeleton. So appearance and acceptance. So if it is quite deadly look, so of course even before wearing it, people become scared of doing that. So if I'm wearing it, so of course anything could be happen to me. So in that case, we have to give that kind of aesthetic look to the robotic exoskeleton so that at least it will go above the acceptance level. So this is a type of exoskeleton based on the actuator. So like active actuator, those like electrical, pneumatic, hydraulic actuator. We have semi-active actuator. These are the specific type of actuator like magnetorheological fluid, antagonistic joint stiffness, the rubber and now coming to the passive actuator. So suppose in many times we may not need a motor. We can use a passive element like the spring or rubber band. So in that case, suppose think about a normal scenario. If we are elongating a spring, and obviously it will provide an opposite force. So sometimes we can use that spring force to create the actuation in the human arm. So the advantage is that, of course, it is lightweight. The next advantage, like it cannot consume any active energy. That means we don't need to use any battery or electrical power for giving this actuation force to the human body. At the same time, there are other types of safe memory alloy that has been developed, specific type of actuator like safe memory alloy and flexible fluid actuator. Okay, so we have, that's what we have talked about, the biomechanics data of human arm, the winter biomechanics. So normally when you are designing an exoskeleton, we have to think about what is the segment mass by the total body mass, because we have to think about the motor for lifting that particular joint. we have to know about like how much distance from the joint to the forearm, from the forearm to the hand, the center of gyration. So all those parameters needs to be considered once we are developing this kind of system. Okay, so this is a project that I have started during my master's at IIST Sipur. So that is a 10 degree of freedom human arm exoskeleton. So I would like to put that slide here because from that point, actually, I have developed this interest of creating this exoskeleton. So that exoskeleton can integrate all the joint motion from the shoulder girdle to the wrist joint. So like shoulder girdle has 2, then shoulder joint has 3 degree of freedom, elbow has 2, and then wrist has 3 degree of freedom like this. So it's very, I would say it's not that advanced one, but it's the kind of giving you a basic idea because it is a purely a master research project which I have done. So how can we develop the exoskeleton while considering the human body structure? So like we can integrate all kinds of joint movements like elevation, depression, flexion, extension, adduction, internal, external motion, like this twisting motion. If you look at my video, look at me, so I'm just twisting. So that kind of motion also we can integrate using this exoskeleton. So this is the human arm Simulink model in MATLAB. So by using this kind of simulation model, we can find out how much torque that joint might need, so that we can select that particular motor that we can fit with that system. And of course, you have to do some kinematic analysis of the exoskeleton because without it, we cannot see like in which way the robot can move, like what are the points they can reach, all the dexterous points. So those are called DH parameters. So if anybody studied robotics, so that is the first chapter normally you have been taught. That's the kinematics and the dynamics and the DH parameter of an exoskeleton. So that actually help you out. Suppose if you are moving an exoskeleton, at how many points the robot can reach. So that can be analyzed by this kind of kinematic analysis. And as you can see, by using this kind of simulation model, we can actually find how the posture of the human arm looks like. So as you can see, we are moving that exoskeleton on the 3D space, and that shows the posture of the human arm while they are moving from one point to another point. The second picture that shows like how many points it can reach. So as you can see, without few places, it can reach almost all the 3D joints in the 3D space. And this is the microcontroller interfacing circuit. So we have used a microcontroller circuit and Philips microcontroller and 2 different controlling unit, one for controlling the BLDC, the brushless DC motor, and one for controlling the normal DC motor. So everything is developed by myself. So it's nothing is bought from anybody. So as you can see from this raw circuit, it's nothing from the market ready software or market ready instrument. And this is the graphical user interface for controlling the joint movements. Now, if I have explained, if you have listened to that slide here, as you can see, we have talked about 2 types of actuator. One is the electrical actuator, like electric, hydraulic, pneumatic, and active actuator that consume energy or the battery power for moving the joint. At the same time, we can have a passive actuator like a spring and rubber band. So that actually can provide all the actuation force without consuming any energy. Now my current research is working in that particular field. How can we create a hybrid exoskeleton by integrating an active and passive actuator, so that we can actually avail the benefits of both the actuators in a single system. So whenever we are using electric actuator, the electric motor, of course, whenever we need it, but sometimes we may not need an electric motor. then there is no point of wasting any battery power for that. So instead of that, we can use a spring power passive actuator for providing this energy force. So this is the way we can create an optimized model of the exoskeleton for a better power resources. So this is the prototype of exoskeleton which I have developed back in Bournemouth University in UK. This is one of the journal Mechatronics and Robotics which are published, and this is the materials. So most of the components are from 3D printed items. So these are the dimension, and the weight is not more than 2 kg, 1.8 kg, and nylon gear materials, and also the spring materials are ASTM. So this is the comparative torque between exoskeleton and joint based actuator. So what I did in terms of a joint based actuation, we have used a slider crank joint model. In a way, we can enhance the torque to weight ratio, because if you see the graph, in that case, the blue graph that shows if a motor is fitted at a joint. So in that case, you probably need 1 Newton meter joint torque. But at the same time, if we use the mechanism which I have developed, that can actually require 0.5 Newton meter. So obviously, less joint torque, less amount of power consumption, less amount of battery resources. So literally, by that way, we can enhance the torque to weight ratio of an actuator. And also, if it is working in the spring assisted mode, in that case, how the actuation, the joint torque looks like. So that's a mathematical equation of the joint torque based on all the joint and structural parameters. And this is the embedded system. So we have taken the current sensor into the consideration, the potentiometer circuit for measuring the joint angle, and from the joint angle, we have calculated all the joint velocity and the joint frequency using the mathematical calculation. And after that, we are fitting into another mathematical equation for developing the joint torque. So, and the DC motor is being used for controlling all the actuation for this exoskeleton. So we have started with using the microcontroller Arduino circuit, but later we have replaced with much more advanced one, the Arduino IoT module, the 33. So that has an inbuilt gyroscope, inbuilt accelerometer, and inbuilt Wi-Fi and Bluetooth facility. So we have also taken few consideration while creating that system, like joint misalignment compensation. So suppose when you are moving our joint, sometimes there's a difference between the pivoting point and the center of joint. So obviously we have to compensate that distance. So that is the reason we have used some compressive spring for that. So I thought better to talk about all those features, because if somebody is interested from the audience, if he or she like to create this kind of exoskeleton, probably would like to do some PhD in future in UK or outside. So this kind of properties, of course, you have to look it around, okay? Because otherwise, you'll face a lot of problems. And these are the arm supporting structure of the exoskeleton for providing the twisting motion, and the shoulder support for actually attaching your whole exoskeleton with the shoulder. And this is the universal joint. So literally, we know the elbow joint is single degree of freedom, but still we have used an universal joint so that we can provide some flexibility to the elbow joint. Let's play the video of the demo. That's my device which I've developed. So it is actually been controlled at very lower speed, because we thought like if anything would happen, then it should not break our arm, because otherwise, that's a bigger problem. So that is why we are actually running it as very lower speed. And as you can see, the exoskeleton providing the whole joint motion. Now, the same exoskeleton has been also integrated with a spring. So what happened at certain point, if we don't need an motor force, we can use a simple spring force for the actuation. Like what? So that you can see as a hybrid mechanism where we are integrating both the motor and the spring in the same model. So whenever we require a motor actuation, we can use it, and obviously the battery power will be utilized. But at the same time, if we want to use this kind of spring power, we probably don't need any battery for that. So, and we can utilize the both actuation in a single model. And the structural formation of these robots, if we are thinking about sensor, we of course we have to think about like a normal sensor that can be used for measuring the human body parameters like angle, can be measured by the potentiometer and encoder. Velocity and acceleration can be measured by the accelerometer. Orientation can be measured by the gyroscope and the compass, and of course the IME unit. We can use some flex sensor for measuring the bending, some torque sensor for measuring the torque one. Also, sometimes if you see most of the autonomous system, autonomous exoskeleton, they sometimes use some biosignal. So biosignal in that sense, that signal that is generated from the human body, like EMG, electromyogram, EEG, electroencephalogram from the brain, myogram from the muscle, and EEG electrocardiogram from the cardiac position. So those kind of biosignal also can be used for controlling all this exoskeleton. At the same time, like the sound and the motion tracking cameras can be used for maintaining its movement. Actuator can be used like an electric DC motor, BL DC motor, stepper motor, or hydraulic and pneumatic actuator at the same time. The mechanism, now if you can think about, we have used a slider hang mechanism. If you see the video, if you are familiar with all the mechanical actuation, but at the same time there is other kinds of mechanism also involved in it. How? Like the serial mechanism, gear drive, belt drive, other locking mechanism, the spring based mechanism, the 4-bar mechanism. Now these are the, as I'm saying from the beginning, like whenever I say these are the structural formation, of course this is quite generic one. So if it is exoskeleton or any kind of system, if it is quite specific one that is being used for a specific purposes, then of course there are more sensor, more advanced mechanism will be involved for developing those robots. Okay. Now materials, if we are trying to create these robots from the 3D printed material like ABS, PLA, or also it can be made from the metal like aluminum. And right now, I think most of the robots either using the carbon fiber composite because that has more strength than steel, but at the same time, less weight than the aluminum. Embedded processor, of course, if we are taking this robot along with us, it also has some processor, whether it is following the biosignal processing and do some action, or if it is doing that automatic action based on the signal itself. So in both cases, we have to use some inbuilt embedded processor inside this robot. So the processors like Raspberry Pi or Arduino that can be used. Arduino, I probably won't recommend. So Arduino can be used for an kind of hobby project. But if you are going towards much more advanced projects, of course, you have to use some ARM Cortex that is proper advanced controller. Okay. Now control system, there are lots of control system like the PID controller, proportional integration and derivative controller. That's a quite usual one that normally people researchers use. There are more advanced controller that is like robust controller, adaptive controller, and now as you know, people are now using that fuzzy control technique, and they are integrating the neural control, the genetic control algorithm inside it. So obviously now the control system, the control algorithm is getting much more advanced with the time. The smart features, sometimes this kind of exoskeleton use like the haptic feedback or AI based monitoring. So artificial intelligence also included inside the controller so that it can also resolve some unknown problem. Okay, and also it can be used for the monitoring purposes. Okay, so this is a kind of simple architecture of a feedback and control system of an exoskeleton. So as you can see, we can take the EEG sensor uh, from the brain to analyze the motion initiation. We can take the kinet sensor. The kinet sensor, we probably, I think, many of you have your this kind of item like the Microsoft Xbox. So normally people buy the Xbox for playing the game in the game console. But at the same time, the Microsoft Xbox can be used as a motion tracking camera. So I think the technical name of Xbox is called kinet sensor. So if we are using a kinet sensor, we can actually track your human body movement using the joint vectors recording system. So through the kinet sensor, we can also record the response of human behavior. We can use the EMG sensor electromyogram that can take the signal from the human muscle. So we can also analyze the motion initiation from the human muscle at the same time. Then we can also take the haptic, the sound sensor. Suppose we would like to create a robot where, like, say, okay, stop. So the robot will stop working. Okay, start. The robot will start working or move. So sometimes you can see a lot of robotic systems that actually use the sound sensor plus sound signal as a command for controlling that robot item. And at the same time, of course, we need to use some other kinds of joint sensor and the position sensor that we can record the joint parameters. So all those sensing signal can be connected using an adaptive controller where we can record all those parameters, and then we can send the actuation signal, as you can see on that figure, to the joint actuator so that we can control that particular joint. So whether the users want to move their joint or not. So based on that initiation, whether we are getting from EEG, EMG, kinet, haptic, joint sensor, combinedly or probably from a single sensor itself, then we can control the joint actuator based on the joint signal. Okay. So this is the types of sensor we can use for controlling the this kind of exoskeleton, like potentiometer, encoder, accelerometer, flex sensor, EMG sensor, EEG sensor, sound sensor, kinet sensor, gyroscope. I've already talked about the functional properties of the sensor, like potentiometer encoder can be used for measuring the joint angle. Accelerometer can be used for measuring the joint velocity or acceleration. Flex sensor can be used for measuring the joint bending. EMG sensor for measuring the joint muscle signal. EEG for the brain signal. Sound sensor for the sound signal, and the kinet sensor for tracking all the body movements, and the gyroscope for the orientation and the tilting position. I've also worked a little bit on the kinet sensor. So how can we track human joint parameters for controlling a robotic exoskeleton? So I have created an audio-visual game, a basketball game using the kinet sensor, where actually the kinet sensor actually tracking all the body movements, and also it is tracking the voice from the users. So it's actually taking my voice and it is putting in the Windows speech recognition, and we have created the whole game in the Unity game engine, and literally from there we are not only controlling the game within some audio visual interaction. So interaction means it is a two-way communication. So when I'm going to play the video, you can see like how the game actually taking the voice signal from the user, and also providing some encouraging words, as you can see. At the same time, we are actually recording all the parameters of the human joint, like velocity, acceleration, torque, position, and the time data using some MATLAB and low-pass filtration technique. So let's play the video, then you can get the idea how this kinet sensor can be implemented for controlling the robotic exoskeleton.
almost reached. We have almost reached. Almost reached. We have almost done. Today we have scored in the draft. We have almost done. Today we have scored.
So as you can see, it is not only providing us like the encouraging words like yes you can do it, yes you can do it, yes almost reach. At the same time, this game also taking that word like a drop, so that actually used for dropping that ball inside the game. So this is a kind of virtual reality now based implemented with the robotic exoskeleton and also for the security purposes as well. Now, actuation selection, as I've told about, like the actuation can be electrical actuation, like motor, passive actuation, like the spring, pneumatic and hydraulic actuation, like the control valves. So, based on what kind of mechanism, what kind of system would like to develop, whether I would like to develop fully based on the motor, yes, you probably don't need to think about like spring or other actuation system. But if you like to think about only creating a passive actuation, then we need to use a spring. If we are thinking of creating a hybrid actuation, then of course we have to integrate all the to the actuation at the same time. And this is a kind of mechanism they can use. You can use like the all this belt, pulleys, locking mechanism, this kind of rack pinion, gear drive, side crank. So these are the, so when if you are studying the mechanical engineering or some other subject, and when you are kind of working towards developing this kind of exoskeleton, so you have to think about a lot, like what kind of mechanism you would like to integrate for creating this kind of system. And of course the microcontroller like Arduino board, Raspberry Pi, or PIC microcontroller. I think right now I can see a lot of researchers, they're using Raspberry Pi for developing this kind of exoskeleton and all this IoT based platform. But at the same time, you can also use some other your inbuilt microcontroller system for your specific purposes. Okay, now this is our geopolitical situation at the moment. So if we are looking at the potential superpower, so obviously it's like the China, the US, they are the main superpower. Then it comes with the Russia, and then the European Union was a superpower before, but after the Brexit, now everybody is dividing between themselves. So of course, I don't think there is they are not a superpower anymore. But at the same time, the other power like Brazil and like other like Israel, they also having a lot of armed forces. Now, of course, we all aware of like the India, like the three sides of the India is surrounded by the water, and on the top side and the left and the right, both side I would say, mostly surrounded by the Pakistan, China, and the Burma. Now, looking at the current situation, when the China, they are trying to infiltrate, they are trying to capture as much area as possible, whether we go to the Simla, Uttarakhand areas, or to the Arunachal areas, like in both places. And of course, the Pakistan, there's a huge problem. We have a lot of clash with them, and then we have Afghanistan right now, the current situation. So looking at all those features, like we have to think about our defense sector in that case, like how we can advance, we can actually advance our military power using this kind of robotic system, so that we can actually face all those troubles together. Now, there is another example I can say, like this is all the cutting edge research is going on currently at the moment. Like the lethal autonomous weapon system is a special class of weapon system that can use a sensor suite and computing algorithm that can independently identify a target, employ an onboard weapon system to engage, and destroy the target without manual human controls of the system. Although those systems are not with widespread development, but this could enable military power operation in the communication degraded or denied environment in which the traditional system may not able to operate. So yeah, this kind of new system, and there is another system that's called Brahma. I think they have developed by Brahmastra. They have been developed by the Indian. So that is a kind of automatic, missile destroyer system. So yes, so these are more robotic system coming into the features. Now, when we are looking at all those robotic system, yes, we have developed few items. There are few items that has been developing currently, and also which is still in the idea still. So they're in the process of development currently. Now, what are the research challenges we are facing? So of course, like without challenges, like people are not like, okay, we have just think about any item and we are going to develop that. It's not like this. We have some research challenges, and if we are using this kind of robotic system for the defense purposes, for the security purposes, there are more requirement we need to fulfill, like portable and lightweight power storage. So of course, like if we are thinking about whether the soldier carrying the exoskeleton or whether the robot carrying itself to the battlefield, we have to think about a portable lightweight system. So that will actually consume the optimal power from the battery sources so that it can stay for a long time. Secure and robust communication link. That means whenever the communication has been made between the robots and the human operator, or the robots actually supply some classified data to the human operator who is actually sitting in the ground station. So that should be secured with some encryption and with some more, I would say, data protection system. And that should be robust as well. And it should be fast. So right now, people are using 5G communication, because what happened, suppose the robot saw a certain enemy object, let's say a tank coming towards it. Now, by the time, let's say, if the processing and the transferring communication is not fast enough, in that case, suppose whether it is taking, let's say, 10 seconds to process that object that is seen by the camera to activate its machine gun or any other missile attack. At the same time, suppose if the communication channel is not fast enough, suppose, okay, the robot sent the signal to the human operator, and by that time the human operator sees it and sending some signal to take the action to the robot, by the time the robot can be destroyed by the enemy. So that is why, of course, you have to think about the secure and the robust communication, but at the same time, we have to think about the fast communication, because it can take the action by the time. So 5G, so most of the cases is use the microwave radio signal, the satellite communication, but we have to think about a lot more advanced type of communication so that it can take the option in a matter of seconds. The real-time navigation in the hazardous environment. So of course, it should have a lot of features, whether actuation, the sensors, so that it can track or it can map on the uneven terrain in some hazardous environment that can have a temperature more than, let's say, beyond the human tolerance, or maybe that probably going through a certain areas where the temperature is beyond, let's say, -50. So in that case, also the terrain is not smooth enough. It has, mountain or maybe like a small tillas and all those kind of things. So in that case, the navigation should be good enough, so that real-time navigation, that's using some other sensors. So I think for the navigation purpose, the sensor plays an important role. Implementation of human-like behavior. So when I'm looking at few bio-inspired robots, so that you can see, like it has the camera. Not only it can walk like a human, you can behave like a human, but at the same time, it has some other components, like one robot, the big dog, that has an serial robot gripper that can pick and place a certain object. So literally think about a human, it can actually do the similar kind of task. So of course you have to think about all those features where the robot can provide or deliver this complex maneuver, the shifting of tools, and also can do the other complex tasks such as like mine disposal, or like some other bomb disposal, neutralize the enemy tank, or other systems. Real-time execution and solving unknown problems. So of course the real-time execution, the processor speed should be good enough, the real-time diagnosis as well, at the same time solving unknown problems. So I have talked about the adaptive control. So even the robot is not been programmed in a way where it is supposed to only facilitate those action which is been programmed, but at the same time it can also provide those action which is not even programmed in that way. I think there plays AI is a big role, the artificial intelligence and the machine learning, where we are trying to train the robot with the big data, with the millions of billions of data. In that case, based on this data and this learning model, they can actually find a feasible solution for an unknown problem. So based on the data. Now, of course, keeping the system safe from the environment and the enemy. Of course, like we have creating a system, and by that time it is not even so. Okay, if it is running for like 2 hours and ultimately because of its own heat it bursts, so there is no point of developing. So of course you have to develop the system, the processor, and the controller in a way we can it does not only keep itself safe from the environment enemy, at the same time if it is actually using for a different purpose, suppose in the battlefield an UAV is used for carrying wounded soldier to the base station. So if does not perform well, and let's say if it malfunction, then of course like it can be happen like in any more casualties could be happen. So those kind of challenges, I think if we are thinking of implementing this kind of robot in a defense sector, whether through an autonomous robot, unmanned robot, vehicle, or like an exoskeleton, which I have more focused on, we have to think about all those properties before developing it. So this is our Canterbury Christ University, the North Home campus. So we have 3 campuses from where I belong. It's established in 1962. This is the Central Library. So North Home campus where my office is, I'm situated. And this is the Midway campus and the libraries. So we have, this is a new school of engineering. So we have secured almost 13.7 million in government fund through the charities. And also we have an different types of framework of teaching we have established here. CDIO framework, which is a problem-based learning approach. And we have also focused on the Industry 4.0. So it's a very lovely city, Canterbury. So if you will get an opportunity to come, please, you can come and I'll be happy to welcome you. This is the Engineering and Edge Hub, which is a new 65 million pound school that has been recently built up just only for the engineering. We provide the higher degree, MScs and PhDs, BTech, continuous professional developments, makerspace. New facilities we have developed like the robots, which I have shown it to you in the video. And this is the framework of teaching we have currently providing to the student, the CDIO, concept, design, implement, and operate. And that is the initiative taken, considered by the world-renowned MIT, Massachusetts Institute of Technology. And Canterbury Christ Church, our university, is one of the few UK universities to be accepted as an international. this CDIO platform. Thank you so much for inviting and for giving me the opportunity and have your patience to listen to this long talk. And I'm happy to welcome any question. I'm not sure like I can answer all those questions, but I'll try my best. Thank you so much, and thank you so much, Jugal, and all the organizing team for organizing this kind of FED. I wish a grand success for the FDP. Okay.
Thank you, sir. So, if any participants want to ask any question, they can please ask, or they can even write their question in chat box. Sir will be happy to answer it. Dr. Somu will be waiting for some time if anyone wants to ask any question.
Yeah. Sorry, I cannot stay for a long because I have another conference. That's an European meeting I'm a part of, so I need to attend. But I'm here for another 5 to 10 minutes. Yeah. So
Yeah,
I'm happy to answer any question.
yeah, we'll be just finishing soon. So let's wait. If anyone wants to ask any question, let's see. But anyways, the talk was really interesting, and whatever experience you were having, like all the practical exposure, that was really wonderful, sir. And I hope,
Thank you, Dr. Jugal. Call me Somo, by the way. I don't like sir. Yeah.
yeah, because
Anybody? Any?
here it's trend, so we have to follow that. But
Yeah. Okay.
anyways, I hope like all the parties, all the learners have learned a lot. Just a second.
Can I ask a small question when
Yes, please.
Dr. Jugan is on phone? This is about the misuse of the quadcopters or any such kind of robotic devices.
Yeah.
Recently, we have experience in Jammu where suspected terrorists,
Absolutely.
probably Lashkar-e-Taiba, were using that quadcopters somewhere in June, 1 or 2 months back, where they used the device in bombing the airport at the Jammu. So the misuse. How can you see? How do you see? I mean, how do you see the misuse of this technology by the wrong people, if I may say so? Or
The thing is like
what are the policies that we have even in India or at the UK or in the United Nations level? How they are going to look at the weaponization of this, this
okay. So
devices?
there are two types. Thank you for your question, Dr. TK Singh. So first of all, we have to think about like there are two ways of using. One is like ethical use, where they're using for a specific purpose with the permission, or they're using unethically. So with the other people like terrorist people, they normally do it. Now, if people want to use it unethically, there is no way you can stop them. But in terms of controlling it, yes, most of the time it has been controlled and monitored by the air traffic controller. So normally, if an unauthorized and like the any kind of moving flying object is been coming into a territory without any permission, so normally what happened, it has been tracked down and normally been neutralized. So that is the way the air traffic controller mostly take care of all those responsibilities. But from other aspects, like also we can create a map where we can actually identify any unidentified object inside those map, and after that we can actually send the signal of its position like the other items we normally do, and then it can be taken care of by the government authorities. Yeah. But yes, so we can use a lot of more sensor, like I talked about that beam. So one beam that can actually cover almost like 3 to 4 kilometers if it's at a certain distance, like the whole areas that can cover. So one of my fellow colleagues back in IST, so he is actually working on this kind of beam, aerial beam, that they have used for the surveillance and the monitoring purpose. But at the same time, they have to take a lot of permission from the air traffic control before launching that beam, because that's what I told about.
Thank you.
Thank you.
Is there any other questions? Thank you so much, Dr. Somu. You have address all the answer, all the questions, whatever sir has asked, because our sir is very active in all the session, I would say, because
Okay,
he
that's
actually ask questions, and his questions are also very critical and very important also.
Thank you.
And if you like to more about this robotics and the exoskeleton, which is my research field, so I can provide my email ID to Dr. Jugal, so you can take him from. So if you'd like to contact me more anytime in future, I'll be happy to answering
Yes,
further questions.
Sure,
yes,
sure. Thank you.
definitely.
Thank you. Sure.
So yeah, Dr.
Thank you.
Somu, now we are going to finish our session. Thank you so much. We are really very grateful to have you in this in our course, and I hope all the participants have enjoyed your session, and hope to see you in other more sessions like this. We'll definitely invite you. Thank you
Thank you.
so much.
Thank you. Hope to see you in future as well.
Thank you,
Thank
sir.
you. Thank you so much.
Thank you so much. So for the participant, I would like to say tomorrow again we will be starting in the morning 9:45. So we are finishing. We are done. We are done for the day. Thank you so much.